this presentation about the effect of shot peening on material by talking about the third main effect, that is surface roughness and morphology. Okay, surface roughness I was discussing about roughness a few minutes ago with some of you, and indeed, it is considered as a side and not wanted effect in shot peening. Why? Because everyone we were discussing, he aims to have a very good surface finishing, a very smooth surface with a mirror-like or something like this. And indeed, I have repeated many times that surface roughness is increased by shot peening, at least if we consider that if we are peening parts that are then subjected to fatigue loading, we are starting from a very good surface condition, of course. Otherwise, it does not make any sense to use a poorly finished part for fatigue. We have seen and remarked many times in these days that indeed this does not make any sense. We have a CES, the surface coefficient, that is 0.3, 0.4, so it means that the fatigue limit will be decreased. So if we are starting from a good surface condition, roughness is a side effect, and it is not wanted. And this is also the reason why, and I can anticipate, some other peening processes have been developed during time, able to reduce or annul the effect of the indentation. And I'm talking about shotless peening processes, where the media are not more the shots or some material media, but is, I don't know, could be water, could be laser and so on, that are able to induce better surface finishing. Okay, but how can we, indeed, from a qualitative point of view, what can we say about the effect of shot peening? We focus now on shot peening again. Larger shot reduce roughness. Okay, indeed, if we must choose the shot diameter and we think to the surface roughness, indeed, larger shot make it possible to reduce the effect on roughness. Why? Because indeed it's clear, if we have a small shot, the indentation will be the force, if the kinetic energy is the same, the force will be concentrated in a small area, and so the indentation will be more severe. If the diameter of the shot is larger, we'll have an indentation that is a bit more flatter, let's say. Okay, but many times we cannot choose the shot just for the roughness. We have other geometrical constraints that limit somehow the range of dimension we can use. The second is higher intensity induces larger roughness. Also, this is intuitive. If we are increasing the intensity, it means that we are increasing the velocity and finally the kinetic energy of the impact. And this will make deeper the indentation and will increase the roughness itself. If we talk about coverage, the other parameter, indeed, coverage can have an effect, but the effect is then finally a bit asymptotic. So the effect of coverage on roughness is not as important as the effect of the shots and the effect of the intensity. Okay, but let me now show you some other cases. Indeed, some cases, let's say, where maybe roughness is not a side effect, an unwanted side effect, where roughness can be used for adding some function to the surface. Okay, indeed, we are used to think about shot peening just for fatigue, and this is understandable, of course, and this is still and will remain the main application of shot peening, of course. But we can also some other application, okay, where shot peening can give a contribution. Let's say here some of these functions can be seen, where wettability, cell adhesion, corrosion. Okay, what is indeed wettability? Here you see these two drops on a hydrophobic surface, because the drop is retained, it's not spread along the surface, it's retained. Okay, and indeed, in this kind of surfaces, the roughness play an important role. Okay, okay, and this is, if we are able to use shot peening to get controlled values of roundness, indeed, we can use this for improving wettability. Or the same for cell adhesion. Cell adhesion, when could be useful, cell adhesion? Say in orthopedic prosthesis. If we want to increase the osseointegration to reduce the probability for possible infection and so on, the roughness of the texture of the prosthesis is important. And shot peening can be used for obtaining an effect like this. Without forgetting that, apart this effect in terms of surface functionalization, still obtaining residual stresses, compression. And so we are obtaining a functional surface with an improved fatigue strength. And for a prosthesis, this is also important. No one likes to have a failure of the prosthesis inside the body because we know the pain it is and the rest, of course. Okay, and if we are talking now about this, okay, indeed, the effect of the surface finishing cannot be defined just considering the traditional parameter, RA, RZ, RT, and so on, and not so just at the microscopic scale. Okay, and now let's see what we have done about surface finishing, surface roughness. Indeed, what we have done is, the first thing is this. Indeed, to develop a finite element model oriented, aimed not only to residual stress calculation, determination, estimation, but also to the estimation of the expected surface roughness. This is a much more intriguing from some point of view. Because why? Because when we perform a finite time analysis, the surface deformation is related to shot peening, to the physical parameter, but also to the choice we have done in terms of finite element simulation, finite element model. Indeed, we have different kind of finite element with linear shape function or with parabolic shape function, and the deformed shape, especially at small scale level, will be affected by the type of element we are using, by the density of the mesh we are using, and so on. And so that is to say that the use of the finite element result in terms of displacement and displaced surfaces is not enough, but we need to have an accurate estimation. And we developed this tool, let's say, that is based on the Abacus modeling and Abacus simulation, finite element simulation, of multiple impact. And when we are talking tomorrow about simulation, we will see how we can do that. And then we are extracting the surface points coordinate from the FE model after deformation. So we are extracting just the surface. And we are treating this result in terms of input of this MATLAB code, where finally, I don't want to go in all these points, but finally, what are we doing with this? We are somehow filtering the input in such a way that the noise, let's say, caused by numerical calculation is somehow smoothened. And we are able in this way to separate what is waveness and what is roughness. Okay, here is a smooth surface. We can distinguish here waveness, that is the larger deviation from the smooth surface. And if we look at a smaller scale, you have the deviation with respect of a perfect wave. This is roughness. Okay, and we have applied this tool, let's say, to our simulation. Here we see some graph, some image taken from after the finite element simulation and filtering of data. And here we have the the data about the coverage in terms of RA and so on. And then finally we have compared what we have done with some experiment. Obtaining an agreement that is good, is bad, sometimes is good, sometimes is a bit more, is not so good. Anyway, it's always confined in between 10, 15, no more than 20%. And considering the difficulty in this kind of calculation, and it is an estimation, this is enough. And this also can be used as an help, an aid to correctly choose the final parameters of shot pinning. Okay. And an improvement of this model can be done by considering the initial starting point. Okay, and about this I will discuss about tomorrow about additive manufacturing, but just to anticipate, indeed, when we develop, indeed, we discussed the disagreement here, the accuracy and the, but anyway, here with this model we are starting with the simulating shot pinning on a perfectly smooth surface, flat without any asperity. In the reality, no, this is not the real condition. We can have a very good smooth surface and it can be assimilated to a perfect surface. Sometimes we have some deviation, we have a roughness that cannot be neglected, even if very good. And so, what can be done is that we can start from a digitalization of the initial surface before shot pinning. After having the file of the digital email, let's say the number, the file of this surface, we can use it as a base for defining the finite element model, and then starting the finite element model of shot pinning, considering the real surface, digitalize the real surface as the input parameter. And in this case, the final result will be more accurate. And this is particularly useful. I will go deeper tomorrow. This is particularly useful when we talk about additive manufactured part. Why? Because we are starting from surfaces that are with a very poor surface quality in those cases. Let me conclude about surface roughness and morphology by commenting some study we have done about in the field of biomedical engineering, let's say, what we have done. That is, the interface is the surface, sorry, is the interface between the body and the external environment, the physiological environment, let's say. And it's important to find, indeed, I talk about the orthopedic prosthesis and with the other artificial devices that are used in the human body, it's important to have the right condition to improve the integration of the external device, the artificial device in the human body. Let's talk about the prosthesis. We have done some experiment on this, also in cooperation with Cambridge University, and these are the results we have got. Indeed, interaction with wetting media. This is the roughness measured with an atomic force microscope here. We consider the not pin sample as reference, conventionally shot pin sample and then severe shot pinning, and this is a confirmation of the higher effect of severe shot pinning in terms of roughness. Okay, here is again roughness, but measured with the other method, interferometer surface roughness, and here is again the same comment can be done. Here is the water contact angle that defines the properties of the surface in terms of hydrophilicity or hydrophobicity. Hydrophilicity means that the angle is less than 90 degrees. Hydrophobicity means that it's more than 90 degrees. This is the scale that is used. If we have a super hydrophobic surface, it means that the angle is more than 150 degrees. Okay, and this is what we see. That is, in this case, Okay, in this, there is an effect both of conventional shot peening and shot peening. Okay, and indeed, which is the difference between these two graphs? Here we have performed both conventional and severe shot peening, and this is after this treatment, but after a final soft grounding to have the same roughness on the different surfaces. So to make it to make a more evident the effect just of the microstructure. And we see that there is an effect, not negligible effect of the roughness of the samples. Why? Because not for the not pin, because everything remains open, especially for the conventional shot pin and something also for the severe shot pinning. Here are some graphs that refers to the biological tests that were done. Okay, indeed, cell density. What is the cell density? The amount of cells that is that attach will remain attached to the surface of the material was 316 L after 4 hours after seeding, and then after 1 day, 2 days, and so more. And what can we see? That indeed the effect of severe shot peening and also is more remarkable in the initial phase of the test. So after 1 day and after and then at the end, after 5 days, everything is aligned. But this is also not negligible. This is important because we know that all the biological processes that can happen must be facilitated in the initial stage. So I'm even not an expert in this biological issue, but anyway, this is referred as a good fact, let's say, a good result. Okay. And here, what is this? Here, this cell spreading and morphology, again, with other parameters, that is the vinculin expression. And here, the effect of pinning is more effective after 1 hour of culture. And as regards the water contact angle, the relation between the water contact angle and the vinculin expression, what we can see is that it's good to see that there is almost linear relation. So we can use the water contact angle for predict to assess the vinculin expression of a cell area. And the cell area is after 1 hour, after 24 hours, is strongly positively influenced by severe shot peening. Okay. And then we talk about cells. If we talk about bacterial adhesion, what can we see? Also in this case, the effect of the treatment are changing by, if we consider the different time. And in this case, so we see after 1 day and 2 days, this is considered here, and we see that also in this case, the effect of the treatment tend to disappear, increasing the time. But for bacterial adhesion, having a reduced bacterial adhesion rate is even more important to avoid infection. And this is obtained by using CSP or SSP. And this is also an encouraging and interesting result for possible application also for this kind of component. Okay. We also, this is not shown here, but we have also performed similar tests on pure iron. Okay, why? Because pure iron is compatible with human body and is also biodegradable. So, and the aim at that time was to use shot peening to control the biodegradation rate in the human body of possible devices, rivets and so on that can be used in orthopedia for fixing the broken organ, the broken bones, let's say. And in the end, also in this case, it's possible to tune the biodegradation rate of this part by using shot peening. And this was also interesting. And if you are interested, I can send you the paper we wrote about that. Okay. Any question? Yeah, there is a question. Oh, thank you.
In this case, slide number, the previous slide, sir, that wettability.
This one?
Well,
No, no, this is.
No, that wettability, sir.
Wettability.
Wettability angle.
Up.
After that.
Up. Wettability, yeah?
Yes, sir. So here actually higher roughness actually gives lower contact angle. Am I right, sir? Here, the SSP is having higher roughness. And
yes, in this case, yes, we obtain this result.
Yeah,
Okay.
and it gives lower contact angle. And lower contact angle means good adhesion.
Good, yes, indeed. The drop is spreading more, yes. And this is related to the result that I show in the other slide, of course.
Yeah, but higher roughness also means that less fatigue life, no, sir? How do we compromise these two conflicting?
Indeed, we must find a trade-off. We must find something that is make possible a better bone integration, let's say, integration to the human body that at the same time is not causing a strong decrease in the fatigue strength. But it's important to notice this also, that if we perform severe shot peening and we ground the surface, so we smoothen the surface, the water contact angle remain almost the same. So in this case, we are improving also fatigue. There is one.
Cell interaction and bacterial interaction, how that is done?
Indeed, cell interaction is good if it's positive. So if the cell adhere, this is good because it means that the integration is going faster.
Yeah.
Bacteria we don't want. We want this is slow, or even to possibly avoiding, because this is the main cause of infection.
Yeah, that is correct.
And to have an antibacterial surface can avoid the use of antibiotics. Okay, and it is important, especially during the first period of implantation. And this is obtained at least for 1 day or 2 days by using this treatment. Indeed, these are, let's say, the first studies on it. These are not optimized, but the results we have got are interesting, I would say, and not well explored. In short peening, everyone is focused on residual stress, but there are many other things that can be exploited as a result of the treatment.
Sir, for cell adhesion, you using the MTTS cell.
Sorry?
For cell adhesion in India, we use MTT cell, this array from the government agencies. For bacterial, what is a cell? You use it in Italy?
The bacteria indeed are I don't remember the name. Maybe I written here.
Because in India, we use MTT array.
These are the bacteria that are used. Aureus and epidermidis. These are for the skin and for some other. But gram-positive bacteria. They are gram-positive bacteria. I'm not an expert on this.
Okay, sir. Thank you very much.
You're welcome.
Sir, again in that cell substrate interaction slide, can you take that cell substrate interaction slide?
Cells. This.
So the previous one.
This.
Yes, sir. Sir, in general, it is from the studies what we could make out is when you increase the surface roughness, normally the cell adhesion would be more. if the roughness is more, cell adhesion is more. But from the second graph shown in the middle of the slide, we can see that cell adhesion, not cell adhesion, cell proliferation. Even for cell proliferation as well, roughness is actually an important parameter. So if roughness is more, proliferation should also be significantly more. But in that particular graph, it can be seen that for a time period of 3 days, cell proliferation is more for NP than when compared to SSP. Similarly, even for the 5 days time period, we can see there isn't much difference between the cell proliferation for NP as well as SSP. But previous studies, what we have seen is when the surface is more, it's having more roughness, it should be having a drastic change in the cell adhesion, cell proliferation, cell attachment, all these aspects. So
Indeed, this could be considered as some kind of conflicting result. That is, for osteoblast viability, this is true what you say. But if we consider the spreading of the cells, that is to say, here the area of the sample that is occupied by cells, in this case, severe short pinning makes sense. So we have more area that is occupied, let's say, that is covered by the cells. This is why, and this is an important factor. If we refer to this graph, to the viability, you are right. The graph says that indeed, in the initial stage, not pinning sample is aligned with conventional short pinning. That is to say that severe short pinning is somehow decreasing the viability from this point of view. Okay. And anyway, in this case, after 7 days, everything is a bit more level. The difference are going to be.
but
be
even, maybe I'm totally wrong, but my understanding is that even that small variation is not what we should see. We should actually see a very drastic difference, because surface roughness for SSP is anyway more than NP, so that there should be actually a drastic change in the proliferation of these cells. Maybe,
But this
yeah, even the cell line matters. The cell line used matters.
Indeed, if we talk about biological property, there are many variables that play a role, and not all of them are considered. Indeed, we would need a much finer result to fully understand this. What we can say is that, indeed, there are some data that, some results that where your comments are fine, but on the other side, from other point of view, the positive effect of severe short pinning is also evident, like this one, or even more for bacteria, especially after short time. The effect of reducing the bacteria, and in my opinion, this is the most important result from this study. That is to say, the ability to reduce the probability of infection in the first stage after the implantation of the prosthesis, something like this. But anyway, these are in vitro studies, of course, so the way to go to in vivo studies and to practical application, it's a long way.
Okay, thank you. Thanks.
Good morning, Professor. Sir, regarding the surface roughness topic,
Yeah.
why is it necessary to consider the real surface state in the FE model for short pinning?
To get more accurate result in terms of roughness. If the initial conditions are not the right one, the final result will be influenced. It's true that, as I said, indeed, if the initial surface is quite smooth, probably the effect is negligible. If this mirror shape, will be negligible. If we consider, and I talk about additive manufactured part, the initial state will be quite different with respect of the smooth surface, and we must consider the initial surface state. Otherwise, also the final result will not representing the situation after additive manufacturing and after short pinning. We need to represent both the steps. But indeed, for traditional processing machine, also grinding or milling, I agree that probably this effect is not the most important one.
Thank you, sir.
Okay, let's move to the next. No, you have a question. Sorry.
So my question is regarding like in these roughness studies, I think all these studies are more focused related to 2D roughness parameters, right? RA, RZ, RT.
Yeah.
So if I was thinking if you are considering a 3D roughness parameters like SA, SZZ, and then it would give more relation or more it will be more close to the actual surface, right?
Other parameters, you mean?
Yeah, like instead of 2D parameters, if you are considering 3D roughness parameters like SA, SEZ.
Yeah, indeed, these parameters are the traditional one. They do not cover all the aspects that define a surface. So some other have been the skew and also the aerial parameters must be considered, of course. Yes, yes. Now we are doing that. In this paper we use the linear one, but now we are considering the aerial parameter for having a better description of the surface. This, yeah, I agree. Okay.
We have purchased profilometer, that's why he's asking.
Yeah.
We have profilometer, that's why.
Ah. No, no. Okay, we can pass to the next presentation. Okay, what's now the next subject? Indeed, we now discuss about, we introduce fatigue, we introduce the shot peening treatment, that is the wheel peeling machine, air peeling machine, the parameter we should use, media, coverage, intensity, the effect, residual stresses, surface work hardening, severe shot peening, and roughness, and so on. Now the next subject is this: how we can consider the effect of shot peening in fatigue design, how we can consider residual stresses, how we can consider possibly the hardness and the roughness in fatigue design method. Okay, and this can be done, and we will comment what the approaches that are commonly, that are today possibly, that is possible today to use, that are available. Okay, so what I'm doing now, indeed, I'm introducing the subject, of course. Then I will introduce what? How the international codes related to product, especially gears, okay, consider the improvement of shot peening. Okay, so how, according to the international code, the improvement, the different behavior in the fatigue behavior induced by shot peening is considered. And then I will discuss, after that, after some comment on this, I will comment the method that are based, the basic method, let's say, based on the Hague diagram, and then more in detail, the local fatigue limit method, okay, and what is the FKM method. What is FKM? FKM is the acronym from a German standard for fatigue design. The name is in German and it's too complicated for trying the correct pronunciation for me, so remain FKM. and, uh, and then the theory of the critical distance. That is a method, a fatigue design method introduced by David Taylor at Trinity College Dublin that can be used, that we use for considering shot peening. And finally, we will, also on the basis of some experiment we did, we compare the prediction, the assessment of the fatigue strength that we can get by using all these methods. Okay. Okay, let's introduce now the subject. Indeed, we already, indeed, shot peening is able to alter, to change the behavior of the treated part under many possible service applications, service conditions. Fatigue strength, of course, fatigue endurance, but not only fatigue. Stress corrosion cracking is also influenced by shot peening. Corrosion and fatigue also, fretting and other one. And indeed, uh, as regard the design method that consider fatigue, they consider shot peening, fatigue is the field where most of the work have been done. That is to say that due to the importance of fatigue and due to the wide application of shot peening in fatigue, the main achievement in design method have been found, have been got in fatigue design. Okay. And indeed, the fatigue design method that considers shot peening and considers sometimes the ability of shot peening itself to prevent crack initiation, sometimes also consider the possibility to arrest microcrack propagation. And it's also true that the main, among the three effects that are due to shot peening, the one that is most widely used and considered in this different fatigue design approach, they are the residual stresses. There is also also in some approach also contribution of surface work hardening is obtained and sometimes roughness, but the main effect is residual stresses. Okay, and indeed, as I said, indeed, we can define maybe 4 different categories of this fatigue design method. The methods that are assumed and used by the International Fatigue Code, the FKM is one of these. The method based on the nominal stress or the local stress. So nominal, what is the nominal stress? It's the stress that you can calculate by using the theoretical theory of elasticity theoretical formula. Local stress means that we are able to calculate the stress at the most critical point by means of some tool, finite element tool or some other, and also method based on fracture mechanics. That is to say, we are considering somehow the presence of a crack and the ability of, and the possibility to stop the crack while it is propagating. Okay, and this is, and the method of the critical distance developed at Trinity College belongs to this last category. But first of all, let me introduce again the effect of shot peening. And again, why indeed? I have already said that maybe more than once, that the effect of shot peening is more relevant if we apply it to notch part. And this is due to the stress gradient. And here, indeed, we have another, let's say, visual, graphical demonstration of this. What is represented here? Here it is represented a typical, let's say, residual stress field in a cylindrical bar, smooth. Okay, but it could be also different. And that is compressive on the surface, along the external surface, and then at the core is tensile. Here what can we see? Here we see the same bar that is in bending. So we can recognize the straight dashed line represent the trend of the applied stress due to bending, okay, the nominal stress, the typical linear trend, is maximum on the free surface, go to 0 on the axis, and then go to in compression on the other part of the cross section. And then we superimpose to this linear trend the residual stress. And we see that this is the overall, the global stress trend. And what can we notice here? That it's true that here, where we have the maximum tensile stress, we are reducing the stress. We are improving, so we are inducing an improvement of the strength. But at the same time, just after the surface layer, nothing is changing, or even something that the stress is smoothly, roughly, is somehow increasing. And so this justifies the limited improvement of the fatigue strength due to the shot peening, to residual stress. If we consider a notched part, we can see here, this is no more linear trend of the stresses due to bending. The gradient is deeper. Here is the residual stress trend, and we see here that after the superposition of applied and residual stresses, we have a much more effective compressive residual stress. Okay, so the stress gradient in notched part positively affects the effect of shot peening. Okay, just to remark what you have already said. And then let's go to the international code. I'm considering especially that the gear code, some American code, AGMA code, the American Gear Manufacturer Association code. And what can, in some point, these code are considering shot peening, and what they say is this: bending fatigue resistance increase about 25% due to shot peening. Is enough? Is good? What do you think about? It's very generic. Probably yes, indeed. It's good that it's approved that there is a positive effect of shot peening on gear strength, bending fatigue strength of gears. About 25% is a bit generic, but it is a code that cannot be different from this. They cannot say, indeed, they cannot say 50%. They say 25%. Why? Because if shot peening is well done, this is what is expected. At least this is expected, the minimum that you can expect. Okay? Without, in any way, they do not say anything about the parameter of shot peening you should use for getting this result, 25%. They don't say which is the intensity you should use, is the coverage and so on. Why? Because also in this case we have many materials. Indeed, gear material are not, the class of gear material is not very wide, but anyway we have different materials we can use, not only steel also. Okay, we can have also different materials. And anyway, this is what the ACMA code said. So good to recognize that there is an effect. So this means that during the design development, we can count on this result officially. On the other side, if we know that if you are performing much more accurate investigation on the effect of shot peening, this 25 can increase. But if we consider contact fatigue, if we consider contact fatigue, the standard gear, the ACMA standard said that resistance can be improved. This is a bit, maybe a bit disappointing. Let's say that we could hope something more than this. But also in this, indeed, contact fatigue is an even more complicated subject with respect of fatigue, because the same problem of fatigue, the same master of fatigue remains, but also the influence of the contact condition, lubrication and so on plays a role, and so it's even more complicated. So the code won't not give you any number. They say if you apply short peening, you will have an improvement. But from a design point of view, the gain we can get from this sentence is limited, let's say. Okay, there is another standard that is from the American Association of Gear Manufacturers that is fundamental rating factor and calculation method for involute, spur, and helical gear teeth. And in this case, the standard only states that the residual stresses, if properly induced, should increase the bending moment lead of gears. And there is a citation to a paper. Consider that the fatigue limit improvement can be around 30%. So this is aligned with the previous one, okay, the 30%. Anyway, this recognizes the opportunity to perform some, this is not referred to shot peening direct, but anyway, the opportunity to develop, to do some treatment that is able to induce compressive residual stressing. Okay, there is another, this is International Standard Organization standard, ISO standard, that this we consider also shot pinning, calculation of tooth bending strength. So we are referring to bending fatigue in this case. They indeed, in this case, they consider that shot pinning is changing not only the residual stress test, but also the roughness. And so they say that for the surface roughness factor, epsilon, YR, is YR can be different if we are considering shot pinning for shot pinned gears. But anyway, they recognize an effect of shot pinning that is quite limited. And also in this case, this is due that they say this depends on the quality of the material. The last point here, the last bullet, shot pinning effect depends on the quality of material and is roughly estimated around 10-20%. This is quite conservative, this assumption, because we know that 10% makes sense for smooth sample. For gear teeth, we can expect something more. But anyway, this is a code, and they are conservative about this. Okay, let's go now to the possible way to consider shot pinning in traditional fatigue design method. That is to say, in method that consider the eye diagram. We have already commented this figure, and we said that here we have in the abscissa, we have the mean stress of the fatigue cycle. Here we have in the ordinate or vertical axis, we have the amplitude of the fatigue cycle, and the different blue line correspond to the eye diagram, the limit for fatigue, for the fatigue limit for different number of cycles. So we can forget about 10 to 5, 10 to 4, and 10 to 3, and we can concentrate on 10 to 6 diagram. And indeed, the triangle, sorry. Okay. And the triangle here define the condition to avoid plastic deformation. That is to say, as you can see here we have the yield stress, both in the abscissa plus or minus and in the amplitude axis here. So what does it mean? That a fatigue cycle, if we want to avoid failure, if it's safe, must lie in this area defined by this perimeter, by these lines. How we can consider the residual stresses in this, with this approach? The residual stress as a sort of initial point, initial condition. So without shot pinning and if we neglect the presence of residual stresses, each fatigue cycle we start from this point, and imagine that this can go at 45 degrees, the pulsating fatigue. This will be the limit. If we are considering the application of shot pinning and the consequent residual stresses, the initial point moves here. And so with the same, the cycle remains the same, inclined 45 degrees, and here it will be the limit point. And we can see that indeed the length of the segment that defines the possible amplitude of the fatigue limit is much larger considering compressive residual stresses. And if also possible to see that we are considering tensile residual stresses, the effect is ROS. The amplitude will be less, will be much less than the condition without residual stresses. Okay. It's clear this concept. So what we can do with the eye diagram, the traditional eye diagram is this. The residual stress move the origin of the cycle and increase the amplitude we can apply before reaching the limit point. Okay, there is another approach that was developed by Mr. Fuchs that is directly related to to short pinned part, let's say. And it can be used just for notched element, notched part. And it's based on the assumption that residual stresses are able also to stop crack propagation. We have already commented this figure, and I don't want to comment it again, but just to recap, the result is this, is that even if we have a residual stress field, even if a crack is able to develop at the notch root of a notched part, it can start growing, but it will be then emerge in a residual stress field. And due to the steep gradient of the stress, okay, soon it will run in a compressive stress field that is able to stop the propagation. So we will have parts that are with some micro crack that is not more running because due to the effect of residual stresses. And Fuchs applied this concept by modifying the Hayek diagram with, let's say, with an approximate approach that is based on this assumption, that is based on somehow on fracture mechanics, but is not considering the fracture mechanic parameters, just the fracture mechanics idea, let's say. And the Hayek diagram for the notched element is modified this way. He said that in each material can be observed a stress amplitude that define the critical condition. And the critical condition are defined as so-called S-cat value, that the critical alternating tensile stress that is a function of the material. And here the estimation of this S-cat for three different materials, high strength steels, and aluminum alloys, 70, 30, and 20. Okay? And the Hayek diagram is defined this way. The line 4 is the line that defines S-cat. That is to say, indeed, what does it mean? That if the amplitude exceeds S-cat, propagation will appear. And so we are not able to stop the already originated crack. But if the amplitude is less than S-cat, it means that the fatigue crack will stop. And if we have an effective fatigue cycle where a part of the cycle itself is in compression, this will not be effective for crack propagation. So the amplitude is considered as the positive part of the fatigue cycle. Okay, so the positive part of the fatigue cycle might exceed S-cat to have crack propagation. And so what can we notice? That if the fatigue cycle is completely positive, the limit is flat and is equal to S-cat. But if we move this way, a part of the fatigue cycle will be in compression, and so the final amplitude we can apply is increased proportionally to the mean stress that goes into compression. And so what we can find is the limit becomes this one. Okay, and the line 3 is this. SA is equal to 2i S-cat minus the mean stress SM. Okay. And line number 2 is, this is a stress cycle that is completely in compression. That is not dangerous at all. Okay. And finally, this is the modified Hayek diagram that we can use for notched part and for short pinned part. That here, this is the complete representation that consider both what we have seen before, then also the limitation to yielding, the triangle again, and we are also considering here that indeed there could be some, for this notch element, there could be some condition for which indeed the crack cannot even generate because there is not, the amplitude is not enough. This means that in this case, we can apply also the traditional Hayek diagram that is based on crack nucleation. And this is this part of the diagram. So this is a sketch. This is the part that continues here is the modified diagram, but we see that since this refers to the original traditional Hayek diagram, and is more than the Fuchs one, and this is referred to crack initiation. If crack initiation does not happen, even propagation cannot start. And so this is the final trend, is this. Tac. And here the limitation is yielding. Okay, here the Fuchs diagram is larger than the traditional one, and so this is the limit. And we can enter this Hayek diagram the usual way, starting from the basic point with the residual stress and then going up according to the fatigue cycle and the ratio between the amplitude and the mean stress. Okay. This is also another way. And then, indeed, this is good, but it's still, indeed, it's still somehow approximate. The local fatigue limit is much more analytical, let's say. It's much more based on formulas and analytical, theoretical consideration, let's say. The method was developed initially in Germany. Eichender and others developed the method. And it's not only for shot pinning, of course, this is for surface hardened materials. And they say that due to the application of our surface hardening process, okay, we can get an improvement of the fatigue limit that is a function also of the geometry of the notch, and in particular of the stress gradient caused by the notch. And the stress gradient, to define the stress gradient, they consider the so-called relative stress gradient, that is sig prime, and as you can see is what? Is equal to the derivative of the stress with respect of the depth, the sigma over the x, over the maximum sigma. So this is the relative stress gradient. Okay. And they say that indeed the fatigue limit of the part is equal to what? To the fatigue limit of the material, sigma Tf, that multiplies this formula that includes that sigma Tf is the fatigue limit in tension, so the axial fatigue strength. And the axial fatigue limit multiplies what? 1 plus the ratio between bending and tensile fatigue limit, minus 1, that multiplies the relative stress gradient over the times the radius of that multiply the radius of the part at an exponent kd that is a function of the material that for steel is generally considered equal or proximate, equal to 0.3. Okay. So finally, some comment, the model proposes interpolation of fatigue limit in bending and uniform axial stress condition on a notched part to describe the local fatigue limit. And starting, indeed, you say this is the relative stress gradient, and we can apply the same concept to a notched part. We calculate the x prime, that is the relative stress gradient. We can do that sometimes with analytical formula, much more frequently by using today some finite element analysis. And then if we know the basic fatigue strength, axial and the bending fatigue strength of the material, we can define somehow the term of this formula and then calculate the fatigue limit of the notched part. Okay. if we consider short pinning, we must also consider the residual stresses. And here there are the same concept is applied to, in a most widely sense, to residual stresses and the prime of residual stresses. Here you see x prime is again the relative stress gradient, nothing is changing. Okay, but before commenting the formula, let's consider the graph here. What can we see here? We see the linear trend, this one, the linear line, the straight line, that represent the stress due to bending in a smooth part without a notch. Okay? Then what is represented here? This line that starts from the horizontal coordinate is the depth. On the ordinate we have the stress. This line represents the so-called local fatigue limit that is calculated by means of this other formula. Okay, this is another expression of the local fatigue limit. Okay, that consider what? The sigma m is the mean stress, sigma res is the residual stress, so the part due to short pinning, plus 4 sigma d over beta k to the second power. See, what is sigma d? Sigma d is the fatigue limit of the smooth part. Beta k is this factor that include alpha k, that in the German nomenclature is the kT, is the theoretical stress concentration factor, and include the property of the material in terms of roughness, HV. And this multiplies the relative stress gradient. And then out of the square root, there is minus sigma m and sigma r. So this sigma ADK is the local limit, fatigue limit of a notched part. And this is represented by this line. Now, the other line, the last one, is this, very steep, and represent the stress due to the applied load in a notched part. And what can we see here? That if we define a graph where we represent the trend of the local fatigue limit according to the formula, and then we draw the applied stresses, if the load is low, we will start from this situation. Increasing the load, sooner or later we will meet this point. And this point is the limit point. If the applied stress is equal to the local limit at the surface, we are going to break the sample. So in this representation, where the point is here, we are going to have a fatigue failure for sure. If we consider, but we see that whatever is the notch, if we have a notch part, this failure will start from the surface. This is the first point that will intersect the local fatigue limit. The same is not happening if we consider a smooth part. This is linear. We start from this condition, we increasing the load, and at the end, the first point that intersect the curve that defines the local fatigue limit is not at the free surface, but is internal. Okay, and this justify what we have already said more than once, that if we are applying short pinning, residual stresses on a smooth part, the limited stress gradient will decrease the effect of the treatment. Why? Because we are able to shift the crack initiation point from the surface to the internal point, but with a limited increase of the load we can apply. That is another reason why to apply short pinning more on notched part, to apply short pinning more to notched part than to smooth one. The effect will be not the same. Okay? And let's go to FKM method. It's clear, sorry, any question about this? It's not easy to explain without a blackboard, this concept. Maybe it will be easier. But anyway, I hope to be clear. Anyway, I'm here for answering your question and possible doubt. It's much easier than if you try on a paper to draw and repeat what I said. Indeed, but just listening to words. Anyway, this is the indeed there is this formula. Indeed, here this is applied, but we could apply also this other formula. That is another interpretation, let's say, formulation of the local fatigue limit. And other can be found in literature, but as I say, the concept is always the same. We, by means of the local fatigue limit, we recognize that after surface treatment, the surface the property of the material at the surface are different with respect of the core, are increased. And we find some formula to define this increment, and then we can draw the trend of the fatigue limit by using the formula that we have adopted. Then if we superimpose to this trend the applied stresses, and we can apply, and if the part is smooth, we can calculate by simple formulas. Otherwise, we must use the finite element code. Okay, and then we can draw on the same graph the applied stresses and see when there is the intersection between these two curves. Okay, and when there is this means this is a critical load according to this method. Okay, any questions? So, good. Okay, let's go. The FKM method. Okay, this is as I said, the FKM guideline is a German guide. It is a reference for design of mechanical combat. And they consider two different methods, both the nominal and the local stress method. Nominal means something similar to the Ike diagram or Fuchs approach, that is, we are using nominal stresses. Local means the previous one, the local fatigue limit approach. Okay, indeed, FKM is not an official code, okay, but is widely used when you have to prove with some report that what you have done in terms of fatigue design is correct. If you refer to FKM, it's generally well accepted. Okay, and it starts from the German experience on fatigue that is recognized to be good, of course. Okay, it's based on some other standards. Okay, indeed, we are currently at the 6th edition. To be sincere, I have not checked if some other edition after the 6th edition has been published, but in any case, I'm quite sure that nothing important has been changed, okay? And let's see what they say, especially focusing on what they say about shot pinning. Okay, indeed, they say that if we have to deal with fatigue, I'm talking about the nominal stress method, okay, how are we considering, we are considering what made the case of interest different with respect of the standard samples, so for the fatigue strength of the material, are considered by means of factors, coefficient factor. So we have shape, size, type of load, roughness factor, surface treatment factor that are considered. Okay, and by specific combination of this factor, a synthetic, let's say, design factor is calculated. This K, W, K, Z, D, or B. The design factor for a rod shape not welded component under tensile load are defined this way. So if we refer to not welded details, in other words, we can define this design factor that include all the different contributions in this way. KVK means the design factor for fatigue. ZD means for tensile load. B means for bending. And here we see these formulas that KF, where we can recognize KF is the fatigue notch factor. KR is referring to the roughness. KV considers the application of possible surface treatment, and this includes also shot pinning. So shot pinning is included in this KV factor. KS refer to possible coating, if any, of course. KNLE consider not linear elastic behavior of the steel, okay, of material, sorry, and if the behavior is linear, still this is equal to 1, of course. And sigma is a factor that is related to the stress gradient, so similar to the relative stress gradient factor that we have considered in the previous approach. So this is the way shot pin is included in the design, in fatigue design for FKM nominal stress approach. Okay. The formula here is reported, is the same. How can we consider the stress gradient? Indeed, we are in the nominal stress approach field now. And so, how can we consider the notch? Only some kind of notch are considered. That is to say, the nominal stress approach does not want that you make any complex calculation. This is not the aim. They give you some table, some graph with common notch effect, notched geometry in such a way, and some number related to this geometry, in such a way that you can calculate the effect of stress gradient and the effect of NKF. Okay, and you must refer to this factor, otherwise the nominal approach cannot be applied. Okay, KV is the surface factor, is defined also for shot pinning and deep rolling. If we have not done any treatment, surface KV is equal to 1. Okay, and if we focus on shot pinning, let's see that FKM consider in a more appropriate way shot pin. That is to say, if we are considering smooth sample, a notched sample, the positive effect of shot pinning is in the order of 10, 20%, 1.1, 1.2. If we are considering notched steel component, the effect is larger. So from 1.1, 10%, even to 50%, 1.5. And it's up to us, to our expertise about shot pinning and the way we have designed the treatment to apply 1.1, 0.2, 0.3, or even 0.5. And of course, it's of the quality control we are using. Okay. And then, indeed, once we have determined this K design factor, K factor, for bending or for tensile load, we can calculate the fatigue limit of the part, starting from the fatigue limit of the material and dividing this latter by means of this design factor. And if you have a welded part, we can use also other coefficient, or if you have a not null mean stress, also R can be included with another coefficient. Okay, if we consider the local stress method, indeed, from a conceptual point of view, nothing is changing. The structure of the formula, you see, is not very different. Again, there are many factors, KF, KR, KV, that consider also in this case shot pinning in the same way it has been considered in the nominal stress approach. But in this case, indeed, what is allowed, we are considering the local fatigue limit. So what we should consider is to perform, this is much more general in terms of application. But if we want to apply the local stress method, we should consider some finite element calculation to verify, to assess, to determine which is the real stress gradient close to the notch. Okay, the other parameters are almost the same, let's say. Okay, so in terms of practical application, for FKM, the local stress method is conceptually similar to the nominal one. Here, more geometries can be used, according to the fact that we should be able to accurately calculate the stress state by means of finite element analysis. And then let's go. I'm not too late. No, I can go. I can proceed over the. Are you tired? No. Have you any question? Yeah. Okay.
Hello. Sir, can I ask previous slide question? The importance of fatigue design and how it's uses in industries.
Sorry.
Importance of fatigue design and how it's uses in industries.
FKM.
No, fatigue design in previous
Fatigue
slide.
design.
And how it's uses in industry and importance of its.
And indeed, when fatigue in many high-tech product system, fatigue is the main problem. So these concepts are applied. Today are generally applied by means of dedicated software that include not finite element, but not only finite element. There is a complex post-processing of the result that include all the fatigue damage estimation, fatigue damage criteria, and so on, to have a fine estimation of the fatigue strength. And the application of short pinning, if you want an accurate fatigue design, must go in this direction.
Aerospace industries like.
Yes, sure. Aeronautic, of course. Especially because in aeronautic, many parts are designed in the finite life region. So we need to know which is the expected maximum number of cycles that can be used before the part is going to break.
Thank you, sir.
You're welcome. Okay, we can proceed. So let's go with the last of these. That is the theory of critical distance. As I said, it was developed by David Taylor at Trinity College in Ireland, in Dublin. And indeed, Taylor started from the fact that since fatigue damage is not interesting just the surface, but interesting a very small layer of material, okay, that is varying with the stress gradient, indeed. Indeed, the maximum stress at the notch root is not the most appropriate choice in terms of damage parameter. That is not different from considering that the stress concentration factor for fatigue is different from the theoretical stress concentration factor. These are all related, but what is proposing something more analytical than just a coefficient. Okay, and so Taylor proposed that indeed the fatigue, the parameter that should be used for estimating the severity of the fatigue load, let's say the stress that can induce fatigue, should consider a finite distance with respect to the surface, that here is called 2 times L, 2L, and we should consider the trend of the stress along this line. And then the parameter that we are using is the average, the integral of this trend averaged according to the length. And the material, this characteristic length is a material characteristic. Okay. And a material characteristic that depend also on the geometry according to the notch tip geometry. And this is the formula. So according to the theory of critical distance, the notched component, the fatigue limit of the notched component can be exceeded, let's say, when the effect is can be determined when we calculate this equivalent stress that come from the integral of the trend of the stress from 0, from the surface to the critical distance to L, of the equivalent stress in the epsilon, in the y, of course. So SL, that is equal to delta sigma, let's say, is what? Is equal to the average of the trend of the equivalent sigma in this critical distance from the surface. And how can be estimated L? L is estimated according to fracture mechanics concept. That is to say, 1 over p that multiply the second root, the second power, the square power of the ratio between the threshold stress intensity factor, delta kth, the minimum value of the stress intensity factor that make possible the crack propagation, over delta sigma, that is the applied stress. Okay? And why sigma equivalent, sigma x? Because if you are in the uniaxial stress state, this is the sigma, the maximum stress, the only stress that is not zero. If we are in a multi-axial stress state, we should consider some criteria such as the science criteria for fatigue strength. Okay? So, delta L is equal to 1 over P delta TH over delta sigma 0, delta C stress intensity value, sorry for the type of the stress intensity factor, delta sigma 0, fatigue limit of the material. Okay. And indeed, how can we consider shot pinning with this criterion? Indeed, we can consider shot pinning in terms of residual stresses by considering the trend of the equivalence, the trend of the equivalent stress, not only in terms of applied stresses, but also in terms of effective stress, that is the sum of the applied and the residual stresses. Okay? And this is, from a conceptual point of view, that's all. And I don't want to go deeper, just to let you know that there is this criterion that can be used. And then let's conclude, and I will not take so much more time from the end, let's say the official end of the lecture, a comparison of the different methods we did. Indeed, we have used 3 different geometries. You see here the smooth geometry, the usual hourglass sample. This is a notched par with, here there is a small fillet radius that is with KT equal around 2. The material is low alloy steel 40, nickel chrome molybdenum 7, and the applied load is rotating bending. In the second case, the material is a steel A95 according to the API code, and the geometry is quite it's quite severe. We have a very severe a V-notch, so very, very severe. And here in the table, you see the different shot pinning parameter we use for testing the different sample, let's say. So we use the name of the series is indicated and the corresponding shot pinning parameter in terms of material and diameter of the shot, steel or ceramic, let's say, in terms of element intensity by varying it from 8, 10, N to 12 element A, and the coverage is for the first series of samples is 100%, for the second one is 400% in one case and very light, and the second case is again 100%. And then we ran this test on this specimen, and then we applied the different method to the same experimental result to see, at least to estimate, at least for this geometry, which is the criterion that is giving the most accurate result. Okay, and to cut the long story short, let's say let's see which are the comment we can do. Indeed, to apply, I was forgetting that to apply the different method, indeed, we have to modify somehow some of them. Indeed, the local fatigue limit proposed by the German guy Exlander was modified with corrective coefficient because it was not taking care of the surface roughness, surface work hardening. And by means of this coefficient, let's say the agreement was satisfactory. Okay. And indeed, we did some experimental, some finite element analysis to consider the surface stress gradient. FKM requires the definition of few parameters, so it's easier to use. This is for calculating the fatigue limit, and this is the main advantage of the FKM. The nominal stress approach categorized the different notch effect, and it's more the notches we used were among the ones that were considered by the nominal stress approach in FKM, and otherwise we had to calculate by means of a finite element code. The theory of critical distance, indeed, we use the science approach because if we consider residual, even if the load is uniaxial, if you consider residual stresses, shot pinning is inducing a biaxial residual stress state. So we had to use, for a final estimation of the effect of residual stresses, we had to use this multi-axial fatigue criterion. Okay. And in terms of comparison, what can we say? That indeed, at least as regards the analysis we have done, the FKM approach is the best compromise between the simplicity of application, the number of parameters is quite reduced, the effort, the experimental effort and numerical effort is reduced, and the accuracy we can get. The critical distance theory is able to provide a good correspondence with experimental results. And indeed, since we are considering not a point, the stress value at a point, but we are integrating the value over a line, over a finite length, indeed, the result is more robust. It's less influenced by possible mistake, inaccuracy in some step of the procedure, especially numerical procedure. So in terms of short pinning, it provides a robust solution to alteration of pinning condition and possible residual stress relaxation during cycling. The local fatigue limit approach, indeed, after the adaptation by means of the coefficient I said in the previous slide, is able to provide accurate results. But indeed, these parameters were good for our test, for making good results, but cannot be generalized at all. So if you are using some local fatigue limit approach, it's better to consider some extra experiment to correctly address the problem of the factors that are not directly considered in the original development, the original formulas of the approach itself. And I'm here for questions, so I was able to remain aligned with the official deadline, let's say. Any question? Now you are too tired and hungry for asking questions.
So the critical stress we are using in the earlier calculations, that is calculated experimentally or from simulations? The SCAT.
SCAT, indeed. This is SCAT, you mean, did it?
Yes.
These are you mean this?
Yes,
SCAT?
yes.
Yeah.
Here.
These are experimental and estimation. Indeed. High strength steel. This is a family. That is a rough estimation. Anyway, for estimation of the effect of stresses. And the same the other one.
So
In the first this method is assumed to be zero. That is, if there is this line was here, and so the diagram was is a very severe, not corresponding to the physical damage program for fatigue. And anyway, this is a estimation. Yeah.
So consider this critical state in the other method, like the theory of critical distance.
Yeah.
So we have the same stress but the distance.
Same, indeed. From a point of view, the meaning is similar, but the theory of critical distance is analytic. So Fuchs, experimentalist, and Raff, let's say, with tools, numerical tool, fracture mechanic concept applied just from a point of view. This was fracture analytical. And so the sigma zero, indeed, this refers to the, indeed, to use this refers to, indeed, it's not intended, even is similar. I would, to be on, I would, can be used because we'll be in the fatigue limit, of course.
Yes.
But just to be on the safe, otherwise you can use the usual fatigue limit of the material as you conventionally determine.